Thank you very much. So this is all this is joint work with Jennifer Park, John Voigt, and Melanie Matchett-Wood. So I'm going to start by talking about heuristics first for class groups, since this motivates a lot of what we did. So and this is an old subject, going back to Cohen and Lenstra, and then it was reinterpreted in various ways by Friedman and Washington, and later Ellenberg and Venkatesh. So let me explain, not historically the way it was done, but just, well, one way of interpreting these heuristics. So let K be a number field, and let S be a finite set of primes. Okay, so non-Archimedean places. So we want to understand the class group of K, how it varies as you vary the number field K. And I mean, as you know, the class group is fractional ideals modulo principal ideals, but that's an infinite rank group modulo another infinite rank group. So in order to get a better handle on what that quotient is, first fix this finite set of primes. And if S is large enough in the sense that it generates the class group of K, then you know that then instead of taking all the fractional ideals, you just need to take the ones in the group generated by S. So, all right. So, okay, so IS mod, say, and then the principal ideal is supported on S. So, okay, so this is so IS is the fractional ideals supported on S. And these are the principal ideals generated by S units. And the point of doing this is that we know what the structure of these two groups. We know the structure of each of these two groups. So, I mean, this is just as abelian groups, the numerator is z to the n, since if n is the number of places in S. Okay, so where n is the size of S, and then we also know the structure of the S units. That's a free abelian, modulo torsion. It's the free abelian group. It's a free abelian group of rank n plus u, where u is the unit rank. So u is the rank of the unit group. Okay, and this is mapped in here somehow. All right, so for example, suppose you want the distribution of class groups of imaginary quadratic fields. So then you would, okay, so K is Q joint square root of D for some negative D. And, okay, in this case, well, then the unit rank is 0, and so the class group then becomes, well, it's z to the n modulo z, some image of z to the n, so it's some co-kernel of some homomorphism A. So, and of course that's given by some n by n matrix. Okay, so then you can ask, okay, what happens as you vary K? So how are these groups distributed? And actually, you can break this up into its pre-primary parts. As we all know, the two torsion acts in a special way because of genus theory. So I'll fix attention to the p primary part for some odd prime p, and ask how is this distributed as. I mean, another good reason here for fixing attention to 1 prime p is because if you don't do that, well, I mean, we know the size of these goes to infinity. So if you ask what's the probability that it's any particular group, the answer will be 0. So, all right, but here we can get actual distributions. Okay, so this is p not equal to 2. And, okay, so so here are two possible answers. So two answers, or conjectural answers. So one is the Friedman-Washington conjecture, which is historically the second one. But let me just state this one first. So that's the distribution of this group is. Well, okay, I mean, we just model it by this. So we just take, except we imagine that this map from z to the n is somehow random. And so what does that mean? So we start with the distribution of this co-kernel of, or rather the p primary part of that co-kernel, as you, for a random integer matrix. Now, you can't take, I mean, you can't, there's no natural probability distribution on the set of all on this countable set, but you can fix attention to the matrices whose entries are with such that all the absolute values of the entries are bounded by some number x, and then, well, then you have just a finite set of matrices, and you look at for that finite set, you choose a uniformly at random, you need to look at the distribution, and then you take the limit as x goes to infinity of that distribution. And then finally, because here I've implicitly fixed n, and there's no reason that, I mean, the class groups, I mean, they won't necessarily be generated by n elements. So it's natural then to take n going to infinity, which is what you would do anyway if you were back here, if you were taking s to be larger and larger. So, all right, so this is the conjecture, which is reasonable based on the arithmetic of that was explained here. So, okay, that's one interpretation of what it should be. The other one, which is historically first, is the Cohen-Lenstra conjecture, which gives you directly what the distribution, what the probability of each particular group appearing is. So for each finite abelian P group, G, you ask what is the probability, and maybe I should say, whenever I say probability, well, you can, I'm thinking of K as being a random imaginary quadratic field, and what that means, of course, is I'm supposed to order the quadratic fields by discriminant and look at all the imaginary quadratic fields of discriminant absolute value up to x, and then look at the probability that it equals G, and then take a limit as the bound goes to infinity. So okay, anyway, so that's what that means. And then the conjecture is that this equals, that it's proportional to 1 over the size of the automorphism group of G. And, well, you can work out, you can also work out what the constant of proportionality should be. It turns out to be this. All right, so, okay. And, well, neither of these is proved, but what you can prove, and this is proved in the paper by Friedman and Washington, that these two conjectures are equivalent. So, of course, this is much easier to prove than either of the conjectures because there's essentially no number theory involved. This is just about finite abelian groups. All right. All right. So that's the warm up. So now let me move on to the main topic, which are elliptic curves. So here E will be, so I'm going to be talking about mostly elliptic curves over Q, and maybe at the end, if there's time, I'll talk about other number fields. So was there a question? No, okay. So So elliptic curves over Q can be written in this form, and you can scale it to assume, without loss of generality, you can assume that A and B are integers. And if you scale it just right, then you can assume that there's no prime such that p to the fourth divides A and p to the sixth divides B, because otherwise you could get rid of it. Okay, and in this case, once you've normalized things in this way, then we can define some sort of naive height of the elliptic curve as just the maximum of 4a cubed and 27b squared. Okay, so that's going to be used for ordering the elliptic curves later, just as we had to order the imaginary quadratic fields. Okay, and the question, of course, is, well, we know that the group of rational points is a finely generated abelian group, and we want to know how the ranks are distributed. And in particular, we want to know whether it's bounded. And this question actually goes, well, it's implicit in a question asked by Poincaré in 1901, who asked, what are the possibilities for the number of points you need in order to generate all the rational points on this? And, well, the current records. All right, so, okay, there are a lot of people in between, but so I'm not going to go through the whole history. First of all, there exists an elliptic curve whose rank. Okay, I'll write rank this way. The rank is at least 28, and on the other hand, there exists. It's also going to be a question not just about isolated examples, but whether for a given rank you can find infinitely many elliptic curves of that rank. And the record for that is that there are infinitely many of rank at least 19. So this is based on some family that exists over some other elliptic curve of positive rank. All right, so let's see. So the way we're going to get a handle on this question is sort of indirect. We're not going to study the ranks. What we're going to look at is try to model not just the rank, but also look at other quantities associated to the elliptic curves and model them all simultaneously in the hope that we'll have more ways to corroborate the results. Because if we don't know how to prove so many things about ranks, but we know how to prove things about other things, we can get sort of indirect evidence this way. And so in particular, what we're going to do, in analogy with the heuristics for class groups, is look at heuristics for the Tate-Shafarevich group, as E varies among elliptic curves. So throughout this talk, I will assume that the Tate-Shafarevich group is finite, since there will be other more questionable assumptions later. So all right. And in this case, well, we know. There's the Cassels pairing. And under this hypothesis, we know that this pairing is a non-degenerate. It's a perfect pairing between these finite abelian groups, and well, it also satisfies. It's also alternating, which means that x paired with x is 0. All right, and now the question is, well, how does this group vary? And well, if you look back at the imaginary quadratic field case, the class group case, we saw down here that it's natural here to fix the unit rank, because the distribution of this, you'd expect it to be different if you change the unit rank. For example, if you look at real quadratic fields, then, well, there are analogous conjectures 1 and 2 there, but the formulas are different. You would have instead of a square matrix, you'd have an n by n plus 1 matrix, and then here you'd have a different, instead of being proportional to 1 over the automorphism group of G, it would be proportional to 1 over the order of G times the automorphism group of G. And so here, the analog is we should fix the rank and ask, given, for that given rank, what's the distribution of the p primary part of Tate-Schafer-Average group as E varies over elliptic curves of rank R over Q. Okay, so, well, there are several answers. So this time there are three conjectures that have been made. So first one was due to Christophe Delaunay, who, in a series of papers, in analogy with the Cohen-Leinster heuristics, he predicted what the probability of seeing any particular Tate-Schafer-Average group is. So this is going to be the analog of 2. So maybe I should say, compare with the Cohen-Leinster heuristics. So here we'll fix a finite abelian P group G, but not just we know that we're not going to get all possible groups here because, we have this extra structure on the group, and this forces, for example, the order of the group to be a square, and so, it forces the group itself to be the square of a group. And so, it's not going to be the same distribution as before. So, in fact, what we should do is fix not just G, but fix G that's equipped with one of these pairings, equipped with a non-degenerate alternating pairing. So alternating is this x comma x condition. So, okay, and then ask, okay, so for that fixed G equipped with the pairing, you can ask what's the probability that the Tate-Schafer-Average group, or its P primary part, is isomorphic to this G. When I write G now, I mean G has its pairing with it. Yes? Oh, yes. So it turns out that up to isomorphism, there's only, once you know the structure of G as an underlying abelian group, that determines the pair. The pair is uniquely determined. Yeah. Well, okay. It's because in my formula I'll need it. So it's true that the isomorphism type of G determines the isomorphism type of the pair G. Yeah, it's a reasonable. Okay. Yeah, it's a reasonable question. Yes. It's because you'll see wait 10 seconds. All right, so it's because it's because the analog. I'm sure you know this. The analog of the Cohen-Leinster heuristic, instead of the automorphism group of G, the abstract group G in the denominator, it should now be the automorphism group of G equipped with its pairing. So we look at the automorphisms of G that respect the pairing, and then have the order of that group. And then there's some dependence on the rank. Just as here there would, if I'd written the general case, there would have been some dependence on the unit rank on U there. So, okay, and then so it's supposed to be proportional to this, and then there's some normalizing factor so that these probabilities add up to 1, and it's known what this is. It's given by this formula. All right. Oh, I think there should be an R in here somewhere. So, okay. So, all right. So let's see. R plus. There. Okay. So, all right. So let's see. So that's one. So that's one conjecture. here's another prediction. So that I developed, well, first in a paper I wrote with Eric Rains, and then later in a joint paper with Manjul Bhargava and Daniel Kane and Hendrik Lenstra and myself and Rains again. So what we did is we tried to find a conjectural linear algebra model. Actually, I guess we succeeded in finding a conjectural linear algebra model, but well, not just the Tate-Shafarevich group, but the entire sequence, the Selmer-Shah sequence. So involving the p to the infinity Selmer group, which is the direct limit of the p to the n Selmer groups for all n. And okay, and then here you have the p to the infinity. So yeah, I mean, and this if you know this information and you know that E has no rational torsion, then this actually, you can recover the p to the n Selmer group by just taking the p to the n torsion here. And so this, I mean, the idea is, of course we wanted to get information about this. So the idea is by looking at all the p to the n Selmer groups together, and we could sort of have one package that would predict everything. And so this, yeah, so once, if you have this, I'm not going to explain exactly what it is here, but it's motivated by some things that are actually provable about the Selmer groups of elliptic curves. So it's not a random guess. So anyway, if you have this, you can look at what distribution it predicts for the p to the infinity torsion in Shah, and that'll give you some distribution. And then finally, there's a model that's also from that same paper that says, well, where you do this. So if you're trying to model, so R is given, the rank is given, and now you choose a large n of the same parity. So this n is like the n in the model at the top here, where you take a random matrix and then you look at the co-kernel of that matrix. So here, except here, instead of taking a random integer matrix, well, because I'm only interested in the p primary part, I'll take a random p-adic matrix. I guess I could have done that there as well. Instead of taking an integer matrix and letting the size of the entries go to infinity, I could have just taken up there the matrix A could have been a matrix with entries in ZP, and you would get the same distribution. So here I'll just take ZP entries. But instead of just having it be any square matrix, I will impose the condition that it's skew symmetric, so that its transpose is equal to negative A, and also then also I want I'll also impose the condition that the rank of the kernel of the matrix over ZP should equal R. Okay, so I have these two conditions. And then we'll take the co-kernel of this matrix, but now this matrix is being thought of as a modular homomorphism from ZP to the n to ZP to the n, given by A, and we take the co-kernel, and well, the co-kernel is not going to be finite because the kernel is if R is greater than 0. So to get a finite group, take the torsion subgroup of this. So that will now be a finite abelian P group, and then it's possible to show that this finite group this finite group carries. There's some, just in terms of linear algebra, it's possible to define a natural pairing on it, it carries a non-degenerate alternating pairing. I mean, that was the point of doing this. I mean, at least it looks like it might be a Tate-Shafarevich group. It has the same kind of structure that a Tate-Shafarevich group would have, and so the guess is that this is the right this is modeling the Tate-Shafarevich group. So we take the distribution of this, and then take the limit. And then again, take the limit as n goes to infinity through the integers of the correct parity. Okay, so, I mean, and as in the class group case, we don't know whether any of these are correct, if any of these three conjectures are correct, but what we can prove, so this is the main theorem of this paper, is that these three distributions coincide. So, well, I mean, so we could be wrong, but then if we're wrong, then everybody is wrong. All right, so, and as I said, there is some arithmetic justification for it, at least in the second one. Some structure about in the Selmer groups that agrees with what we conjecture there. Okay, but on the other hand, we don't know. I mean, what we don't know is, I mean, we don't have, for the Tate-Shafarevich group, we don't have any explanation like this one here, I mean, here we could kind of see why the class groups should be like the co-kernel of an integer matrix, but we don't have anything like this. I mean, it sort of hints that there should be some structure in the Tate-Shafarevich group. I mean, why should it look like the co-kernel why should it look like the torsion subgroup of a co-kernel? We don't know. Although there's also been work of Christopher Denninger, who is also conjectures that he has related conjecture about the ranks of elliptic curve, how they should be related to the dimension of an eigenspace of some infinite dimensional operator. That's also related to this, although it's coming from a completely different direction. So anyway, I don't quite know what. Yeah. Anyway, we would like to have a better arithmetic justification for this, at least for this model here. All right. So, but now, I mean, this is so far I've been just talking about the Tate-Shafarevich group, and what we really want to know is what the distribution of the ranks are. And so, so this gives some clue because the rank is showing up here, at least in this third model. It's showing up as the rank of the ZP rank of the kernel of a matrix. But here, I mean, in this thing, we fixed the rank R at the beginning, and then we conditioned on the matrices satisfying that condition, having that rank of kernel. So, well, that suggests what a model should be. So, I mean, the idea is we want to figure out what's the model that's somehow the simplest possible that would explain all of these phenomena. And so it's like an Occam's razor type of argument. So we want to model an elliptic curve, and eventually we're going to have to model it according to what its height is. And the question is how do we model the rank? So okay, here's the first attempt. Well, here's the model. So you choose an n by n matrix over ZP. Well, an alternating matrix. So. Oh yeah. So I guess I fix. Yeah. So okay. So fix P. Yeah, the P is going to disappear soon, so, okay, fix prime, yeah, okay. All right, so then, so choose this, and choose it at random, with respect to, I mean, one of the nice things about working over ZP is that you have a Haar measure, so it makes sense to, I mean, as opposed to a countable set, you can actually choose something uniformly at random. Okay, so you choose this at random, and then look at the distribution. So, but the point is, we do not condition on the rank of the kernel. Instead, we choose the A first, and we look at what rank of the kernel comes out. And so that's right. So look at the distribution of this rank of the kernel, with the idea that this rank of the kernel should be what's playing the role of the rank of the elliptic curve. Okay, well, I mean, this is fine. I mean, you can do this. But you don't get very much information out of this when you do the... I mean, for example, if n is even, then most of those matrices, most of the n by n matrices, most of the n by n alternating matrices will have non-zero Pfaffian, or non-zero determinant, and then the rank will just be 0. So, and that will happen off of some lower dimensional variety. And so, and if you're looking at the Haar measure, then the lower dimensional variety will have measure 0. And so, so the result is that with probability 1, this rank of the kernel will be 0, yeah, at least if n is even. Well, then, because it's an alternating matrix, it always has to have, I mean, it always has to have the rank of the matrix, which is complementary to that rank, will always have to be even. So if n is odd, then there's forced to be some kernel. But anyway, but this is what you will get if you just take this. So, which is fine. I mean, this is what, I mean, if you choose n to be a random parity as large n, then, well, this might suggest to you that then, okay, maybe 50% of elliptic curves have rank 0 and 50% have rank 1, which is, I guess, what people believe. But, I mean, this doesn't tell you anything about the elliptic curves of rank 2 or more, because in this model, all those events are probability are 0%. And so we need a more refined model in order to say what's happening inside that 0%. So, all right, so here's a more refined model. So we don't want these higher rank events to be of literally probability 0. So instead, what we'll do, so we'll still choose. Okay, so I'll choose a large n of random parity, because I want this to. I mean, this should be like choosing the root number. And we expect that it should be uniformly distributed, so we choose the parity to be uniformly distributed. And then we will choose a matrix. So, well, depending on the elliptic curve we're trying to model. But except now we're going to do, okay, so here's the key point. Instead of looking at p-adic matrices, we go back to thinking about integer matrices. But integer matrices whose entries are of a size that depends on the height of the elliptic curve we're modeling. And the point is that if you have matrices whose entries have a bounded size, then there's still some finite probability that this matrix will have, say, 0 Pfaffian. It's a positive probability, but it depends on the height of the elliptic curve. So yeah, so we'll choose this matrix. So although asymptotically, as the height goes to infinity, it'll be density 0 to have this rank be larger than 2. It will still be some finite. You will be able to quantify the rate at which it goes to 0 as you increase the height of the elliptic curve, and so that's the idea. So we choose the matrix subject. Well, it should be an alternating matrix still, subject to this condition, and also okay. And then the entries, as I said, the entries should be bounded by some quantity x. And so here. Well, there's some unspecified parameters here. So first of all, well, n is going to be one of the parameters. It should somehow grow as the height of the elliptic curve you're modeling grows. And also the entry size should also depend on the height. And so here, these are two functions. Okay, so these are functions to be functions to be determined. So in order to fully specify the model, I'll have to tell you what these functions are. And so that's going to come a little bit later. All right, so once you've done that, so you can think of this matrix A as being a random variable. I have one of these random variables for each elliptic curve E. And so it's sort of analogous to what you do in the Cramer model for when you're modeling prime numbers, where you say each integer n, you say it's a prime with probability 1 over log n or something, and so you have this. But if you choose them all independently, you get some sequence of numbers that looks sort of like the prime numbers, and then you can prove various things about that model, and you pretend that you're proving things about prime numbers. So I'm going to do the same thing here. I'll define some random variables in terms of these, and I'll give them suggestive names, and I'll prove theorems about them, and I'll pretend that I'm actually proving theorems about ranks of elliptic curves. So define random variables in terms of these. So first of all, there'll be the pseudo Tate-Shafarevich group, which will be. I'll put a prime. The prime indicates that there's something pseudo about it. And this will be the. I'll take the co-kernel of my integer matrix and take the torsion subgroup. And then analogously, I'll have the pseudo rank, which is I'll just write rank sub E. And the prime again denotes that this has nothing to do with elliptic curves. It's really, these are just linear algebra objects. So this is just the rank of the kernel of the matrix. Okay, so we've defined these random variables. So this A is one matrix for each elliptic curve, so I choose them independently for each E. And so you can now, you can prove things about these random variables. For example, here's a proposition. You can say that with probability 1, if you choose one of these for each elliptic curve, you can ask about how many of them have pseudo rank 1, say. So you can prove, for example, that with probability 1, if you take the number of elliptic curves, these are actual elliptic curves, but the random variables have nothing to do with the elliptic curve except for they depend on the height. So you choose the number of elliptic curves whose pseudo rank is equal to 1, and you want to know the density of these, so you can look at how many of them have naive height up to some bound b, and then compare that to the total number of elliptic curves of height up to b. That's how you measure density. And so you can prove then, for example, this is an easy result that the limit of this is equal to what you would expect it to be, namely 1/2. So you should specify the function. But for this you don't need to specify much. They should be, if n is slowly growing. So I should say that for suitable. Okay, so for suitable n of h and x of h. So x of h should be growing. They should be increasing functions, and n should not be growing too quickly, and x should go to infinity. They're functions, they're going to be functions of the height, which is itself a function of E. So h is, so this is supposed to be, Yeah, so this h is supposed to, given the elliptic curve, you're supposed to take h, which is the height of E, and plug it into these to figure out what n and x are. And then that determines where you're supposed to sample this matrix from. Yeah. Okay, but that's already, this is the boring consequence that we already had in the first model. And so what we really want to do is see what happens, how likely is it to have higher rank, and what is the rank distribution there? So now, in order to do that, we'll need to prove some things in linear algebra, because we'll need to know if you choose integer matrices like that. I mean, what do you expect about the ranks of the kernels of those integer matrices? All right, so here's the theorem about this. So suppose you fix an integers rho and n, and rho is going to be the rank of the matrix, which is complementary to the rank of the kernel, and you can ask how many. So of the blank, so there's going to be a blank there. How many of the matrices have rank less than or equal to rho? And how many matrices are there? Well, if I'm looking at entry size up to x, and I have n by n alternating matrices, skew-symmetric matrices, well, there are this many entries, n times n minus 2, n times n minus 1 over 2 upper matrices, because you only have to specify the upper half, and ignoring constants that depend on n. So asymptotically, as x goes to infinity, this is how many possible matrices there are. And the question is, how many of them have rank less than or equal to rho? So as x goes to infinity. So what's the asymptotic growth rate of this? And so we prove that the answer here is x to the n rho over 2. And this was actually quite easy for us to prove, because most of the work had already been done in an earlier paper by Eskin and Katz-Nelson in 1995. Well, they wrote a paper, instead of alternating skew-symmetric matrices, they proved it for symmetric matrices. But well, as you can probably guess, if you know how to prove this for symmetric matrices, it's not so hard to do the same thing for anti-symmetric matrices. All right. Okay, so if you accept this, well, which you should, since it's a theorem, then you can prove that for each r greater than or equal to 1, you can say what's the probability that this pseudo-rank is greater than or equal to this r. I mean, that, because of the way the pseudo-rank is defined, this is the same as the probability that the rank of the matrix is less than or equal to n minus r. I mean, there's always this confusing thing about there are two ranks. There's the rank of the matrix, and there's also the rank of the kernel. And as you know, there's this famous theorem that they add up to n. So this is, all right, so this, and then by the theorem that I just stated, this probability is asymptotically, as x goes to infinity, up to something bounded. It looks like this. So, and if you simplify that, then that becomes 1 over, well, x to the n over 2 raised to the r minus 1 power. So this is supposed to be the probability of having rank at least r. It should be grow this, except, well, I mean, there's still this I mean, this doesn't really say anything yet, because we don't know what x and n are, these functions. Yeah, so this is as right. Okay, there should be constants depending on n. So that's well, but I will. I mean, eventually I will really only care about what happens for one. I mean, one n really at a time. So I'm not the model is not so precise as to say exactly what the constants are. But this so far is as. This is for, okay. So, all right, so, but in order to say, yes?
In your theorem, what is at least row and why is there a question mark?
I don't know why there's a question mark, but.
The word rank is missing.
Is there,
Yes.
Have rank. Oh, yes, that's right, a good question. Maybe that's why there was a question mark. So, all right, so rank. Okay, now I can put a period on it. Okay. All right. Okay, so any other questions? All right, so what I want to say now is how do you figure out what functions x and n are supposed to be? Because that's essential to know what these probabilities are. So, all right. So is it possible to, I know. And the idea for doing this is to look at the is to use that we have not only, this model predicts not only the ranks, but it also predicts the Tate-Shafarevich group. And for the Tate-Shafarevich group, there are some theorems, or at least conjectures in some cases, about how the Tate-Shafarevich groups should behave. And so using that, we can get information about what the size of these entries and so on are supposed to be. Okay, so, all right, so now, this section, it'll be the calibration of the model. So, calibration of these unspecified functions, x of h and n of h. So, okay, then the question we're going to ask of the model that's going to determine this is how large is the Tate-Shafarevich group on average? For this question, I'll just look at for rank 0 curves, rank 0 elliptic curves over Q of height approximately h. So to be precise, let's say height in some dyadic interval. So we're going to answer this in two ways. One with the model. What does the model say? And then what does reality say? And then to make them match, we will set the functions. All right. So let's first look at the model. So now we're looking at the pseudo-SHA and asking how large do we expect that to be in the case where the rank is 0? So what are we doing here? What is the definition of this? We're taking a co-kernel of the square matrix now, of an alternating matrix, and the matrix is of rank. The rank of the kernel is 0. So we're looking, but that's what would happen anyway if you just chose a random n by n matrix where n was even, and you most of the time it would be. The Pfaffian would be not 0. And so we want to know what's the size of the co-kernel, and that's the same as the order of or the absolute value of the determinant of that integer square matrix. And so now we're just asking how big do you expect the determinant to be if you choose an n by n matrix alternating with entries of size about x. And that's a polynomial of degree n in the entries, and each entry is of size. Yeah, so this is a polynomial of degree n in the entries. So and the entries are of size up to about x, so you expect this on average to be about x to the n. And so, all right, so the average, so with probability 1, if you average these over all the elliptic curves of height in this range, this will be of asymptotic to some, well, there might be some constant depending on n, but it'll be essentially x to the n. Okay, so that's the model. That's what the model predicts. And how about reality? So this actually goes back to some old, so this has been analyzed. I guess the first person with this idea was Lang in 1983, and other people have looked at it since then. So Goldfeld and Shapiro in 1995, and Marc Andree, 2007, and so on. Okay. So the idea here is to look at the Bertrand-Sorensen-Dyer conjecture and to solve for SHA in it. So I mean, in the rank 0 case, what does SHA say? So BSD, or sorry, what does BSD say in this case? If you take the L value, it's given by this formula involving all these different things. So the SHA, the real period, the Tamagawa numbers, and then the rational torsion. Okay, and now how big are all these things? So first, okay, well this one's easy. Easy once you know once Mazur has done all the hard work. So you know this is at most, well I guess so the square is at most 256. Okay, but that's bounded. And how about that? This is also relatively easy. I mean, if you know the height of the elliptic curve, then that gives you a bound on the discriminant, and that gives you control over these things. And then the C sub p's are essentially like, for each C sub p is like the exponent of p and something. So these are sort of logarithmic in the discriminant. So well, anyway, you get that this whole thing is about. You can prove that it's essentially negligible. As far as fractional powers of the height go, this is negligible. And also, the L value itself is conjecturally, it should be about 1 on average. So in any case, this would follow from the generalized Lindelof hypothesis, which would follow from various Riemann hypotheses and so on. So I think most people would believe this. And I guess there's also the question about whether this formula is true anyway. So that's also a question. But anyway, but if you accept all those things, then the only thing that's going to affect the rate of growth of this is the lowly real period. And so but that does have an effect. So that means that on average, the size of SHA for these rank 0 elliptic curves should be, well, up to factors that are negligible, namely h to the little o of 1. This should be, well, it's the inverse of the real period. And you can just analyze using elementary analysis how large that should be. And that's going to be essentially, it's essentially going to be h to the 1/12. So, right. So so we have reality on this side and the model on the other side. So now you match them up and you say, okay, well, I still don't know what the functions x and n should be individually, but at least I know what x to the n should be like. So, all right. Oh, actually, maybe I want this one. Okay, so now given that, I can now plug that into here. So choose these functions x and n so that x to the n is essentially h to the 1/12. And so when you do that, when you plug that into this, now this becomes 1 over h to the r minus 1 over 24. And so this now represents the probability, well, that if you take an elliptic curve of height h, that its pseudo rank is at least that its pseudo rank is at least r. So I mean the probability that it has high rank goes down as the height grows, which is what you should expect. All right. So now I can based on this I can give you what the final predictions of this model are. So now it's going to depend on how quickly the heights of elliptic curves grow. But that's an easy question. I mean, how many elliptic curves are there of height up to h? Okay, so an easy proposition is that if you take the total number of elliptic curves over Q of height up to h, well, this is just counting the a's and b's up to some, well, you have to sieve out some of them for the conditions about the prime numbers, but it's essentially this many a's and this many b's, and so it's, well, let me write it like this. It's 20 over 24. So then you can prove a theorem. So this is an unconditional theorem, but unfortunately it's only about pseudo-rank. So with probability 1, yeah, it's probability 1, so it must be correct. So then for fixed r greater than or equal to 1, if you count the number of elliptic curves of height h that have pseudo-rank greater than or equal to r, then that's going to be asymptotic to, well, essentially you have to sum over all these elliptic curves of height less than or equal to h, and then for each one you look at the probability that's up at the top board and the lower right of the top board of the probability that it gets counted in this. And so then that will be, well, it'll be h to the, well, if you do this sum using this fact that we know the rate of growth of the number of elliptic curves, you'll get this if r minus 1 is less than 20, and then it'll be finite if r is too large, then this will converge. This sum will actually converge, and so that happens if r minus 1 is greater than 20. And if r minus 1 is equal to 20, it's too close to call, because it's just h to O of 1, and little O of 1 could be positive or negative, I suppose. So we don't know. Okay, so in other words, that is, we expect that the number, for example, of the h to the 20 over 24 elliptic curves, h to the 19 over 24 of them have rank or pseudo rank at least 2, and 18 over 24 have have rank greater than or equal to 3. And well, you can see where this is going. So the corollary is that with probability 1, the pseudo rank is less than or equal to 21, well, with finitely many exceptions. Okay, now I should say also that Andrew Granville had a different heuristic for elliptic curves, for boundness of rank of elliptic curves. That was based on looking at a family of elliptic curves and looking at the total space of that family and trying to count rational points in a big box and showing that in the whole space, if there was one elliptic curve in that family that had high rank, it would contribute more rational points to the whole family than you would expect by some heuristics in the direction along the lines of Manin's conjecture. And so, and the bound he got it turned out it was also 21. So we're not sure if that's a coincidence or if it means something, but anyway, it's.
Really, few, but it doesn't suggest finitely many. It suggests that there are very few, but not certainly not finitely many.
In his
Arguments.
Oh, in this argument here. Well, I mean, this is a theorem. I mean, if you have this. No, it's a correct theorem. It's just that it's a pseudo rank. It's not the actual rank. So this is a theorem. But yes, I mean, of course, the real question is whether this pseudo rank has anything to do with actual rank. But
Is it well-defined rank prime?
yes, it's a random variable that depends on this choice of this random matrix.
But random is smaller than one into exceptions.
It's like a Borel-Cantelli kind of theorem. It's at least what's written on the board is okay, I think. We prove this in our paper. So it's just, but of course, yeah, the real question is whether these random variables model have anything to do with reality of the arithmetic of elliptic curves. Okay, anyway, I'm out of time here, and yeah, so thank you for your attention.
Well, thanks very much, Bjorn, for a great talk. Does anyone have any questions or comments? So you need to use the microphone.
Since the model is about a billion groups, and it sounds that you will be able to do something similar for a billion varieties. I mean, that it will not be essentially more complicated.
Yes, in principle, you should. I mean, I'm not. Yeah, in principle, you should be able to say something for a billion varieties too. I mean, we didn't try to do this, but yeah, I suppose you would want to have some idea about. I don't know if anybody has actually worked out, for example, what do you expect for the distribution of Tate-Shafer average groups of abelian varieties over Q, for example. Do people know what to expect about the rate of growth of those, say for rank 0 abelian varieties over Q? I don't know. Okay, so the question was, in the abelian variety case, do you have a problem with the possibility of you have different kinds of polarizations, and so it's not even clear maybe what the family is. So, yeah, I guess that is a problem. Yeah, so I don't know. Yeah, so there are several issues that would need to be worked out. But I mean, if you forced me to guess, I would still guess that for a fixed dimension of abelian variety, I would still guess that the ranks are over Q, that the ranks would be uniformly bounded. But but that's just it's just a guess.
So it's the only thing that's specific to elliptic curves, this kind of reality of the inverse size of the sharp in this argument?
I guess so. Well, I mean, there are also things like the number of elliptic curves. You'd also have to work out the analog of this, I suppose. So.
Probabilities, then you would expect period depending on how you have to calibrate your X3N.
Yeah, so, yes, okay. I guess, yeah, there's definitely, we would have to do more work to see what's happening for abelian varieties.
I have another question.
Yeah.
Or maybe two, but so I don't remember what the largest rank is of a one-parameter family. I mean, over P1.
Over P1, over Q adjoined T,
Yep.
then there's a family, so Elkies also has a family over that of rank at least 18.
Okay.
And he
so
can get to 19 by replacing the P1 with an elliptic curve as a base.
Did you check that this doesn't contradict your heuristics? I mean, that you don't get too many curves of rank at least 18 in this way?
Oh, I guess I didn't actually check that, but I'm quite sure that the elliptic curves in that family, that their heights are growing rather quickly.
So you should get some power of.
I think it's okay. But that would be a thing worth checking. That's a good point.
Okay. The other thing is that you said at the beginning that if you would have time at the end, you would say something about elliptic curves over number fields. So maybe.
That's true, but I didn't have time at the end. But
Maybe there's time now.
I mean, you can define the analogous thing, although there's something special that happens over other global fields, and that if you have elliptic curves that are over the number field, but they actually are base changes of elliptic curves over Q, then in certain circumstances their ranks can be rather large. For example, for certain elliptic curves over Q, if you look at how their ranks grow in some anticyclotomic tower over some quadratic imaginary fields, and there are results of Mazur that show, proved using Higner points, that show that the rank can be, that there are ranks that they're comparable to the degree of the number field. So you can, for example, you can find, okay, maybe I can just write one theorem on the board about this. So we can prove unconditionally, actually we have two proofs of this. There exists number fields K over Q of arbitrarily large degree such that if you take the lim sup of all the elliptic curves over all elliptic curves over K of the rank of the elliptic curve, then this is at least, well, okay, we have two proofs, one of which gives this and one of it which gives this without the over 2. So one way to construct such, so you can find elliptic curves, so you can find a number field, for example, for which we can prove that there are infinitely many elliptic curves of rank greater than 1,000,000. So one way to do it is to choose, K in some level in an anticyclotomic tower over a quadratic field. Another way to do it is to choose K to be a multi-quadratic extension over Q. You start with Q and you adjoin a bunch of square roots. And then the rank of an elliptic curve, if the elliptic curve comes from Q, then the rank over K will be the sum of the rank of E and all these quadratic twists. And with some work, you can control the root numbers, and you can use work of Bhargava and Skinner and Wei-Zhang, and also some combinatorial results, some multidimensional Hales-Jewett theorem. And by combining all that, you can prove, again, that unconditionally that the ranks of those elliptic curves is large.
What your result suggests would be 21 times the degree, so that is not contradictory with that.
Okay, but I think actually if you go through the argument, you actually get not 21 times the degree, you still get 21, it seems. So I know, for elliptic curves. Oh, for abelian varieties, it should be different, yeah, so. Yes, maybe that's right, yeah, so I don't know.
So there is this example of Shioda of a family over C of rank 60-something, I forget.
Yeah, I know what you're talking about. Yeah, so so the question is, what is this example of? There's an example of Shioda. Let's see. So Shioda found an elliptic curve over C adjoint T of rank at least 68. And so, I mean, implicitly, I mean, it's actually over Q bar adjoint T. And so it's actually over some number field adjoint T. And so by specializing, then you can get infinitely many elliptic curves over that number field of rank at least 68. So at least for some number fields, yeah, so, and even if you exclude the elliptic curves, so okay, well, maybe I should say that what I think you should do is exclude the elliptic curves that are actually definable over a subfield, a proper subfield. But even then, if you take the lim sup over the elliptic curves that remain, Schrödinger's example shows that at least for some number fields, you'll get at least 68. So 21 is not always the right answer. Actually, I'm not even sure I believe 21 is correct for Q, but I believe there should be some bound. I mean, because as people have pointed out, that there are families in which, it might be that there's some special families that have extra arithmetic phenomena that are not taken into account by the model, and maybe within those families they're higher. You can get higher rank. But okay.
So can the model cope with thinner sequences of elliptic curves? For example, if you were just looking at Mordell curves, can you make predictions for boundedness of rank in?
So Mordell curves, those are the ones where you have what, y squared equals x cubed plus d.
Yep.
Yeah, or something. Yeah. So you can do the same heuristic. I mean, the only difference is that the heights of these grow faster than if you're looking at the heights of all. I mean, you have fewer curves of bounded height here in this family. But you can do the same heuristic, and we do this in our paper. You get a number that's smaller than 21, and if you restrict attention to this family, just because you have fewer elliptic curves essentially of bounded height.
It's compatible with this random matrix predictions?
Well, yeah, the random matrix predictions, I guess they also predict this h to the 19 over 24, for example, and they don't say so. I mean. They're not so precise about what happens later. On the other hand, in this case, they give a much more precise estimate for this. Not just, well, in particular, I guess they actually look at a family of quadratic twists, but they get not only the main term, but they also say like what the power of log is even, and so they're much more ambitious, I guess, in that sense. At least but they don't say things about the higher ranks. That's mainly, I mean, there's several different predictions for rank 3, and they're all contradicting each other. So, but for rank 2, everybody sort of agrees that this is the right thing, I think.
Okay, well, maybe we'll save further questions for the diminishing coffee break. But let's thank Bjorn again for a great talk.